Hi everyone, welcome back to my channel. In today's lesson we're going to discuss longitudinal waves. More specifically, we're going to talk about the properties of these longitudinal waves and then reflections and echoes. So let's discuss what longitudinal waves are. Longitudinal waves, once again, are examples of mechanical waves. Mechanical waves because they need a medium to travel through. A medium simply means it needs particles. If there's no particles, there will be no mechanical wave. So what's the definition for longitudinal wave? It's a wave in which the particles of the medium vibrate parallel to the direction of motion of the wave. So what this simply means is, while this wave is moving in one direction, let's say to the right, the particles are going to vibrate parallel, meaning they're going to vibrate left to right as this wave is moving to the right. So as you can see in this, let me just see here, as you can see in this example, as the wave is moving to the right, the particles are vibrating left to right, left to right. So let's look at some properties of longitudinal waves. First thing that you will see when you see or observe a longitudinal wave is that there are a region of high pressure and there's regions of low pressure. High pressure meaning there where the particles are very, very close to one another, and low pressure is there where they are spread out. Now, where they are very close to one another at a high pressure, we call it a compression. The place where they are very spread out, far from one another, is what we call a rarefaction. So, compression, region of high pressure, while the rarefaction is a low pressure area. Then, the second one we also talk about is wavelength. So, longitudinal waves also have a wavelength, but from where to where does a wavelength stretches? It stretches from the middle of a compression to the middle of a next compression. That's a wavelength. Same for middle of a rarefaction to the middle of the next rarefaction. That is where one wavelength stretches. So let's say it stretches from the first or the middle of the first rarefaction to the middle of the third rarefaction, then it means there are two wavelengths present in this wave. So once again, here you can see the vibration of the particles is left to right, left to right. That's because it's parallel to the direction of motion. And then the other property is the amplitude. So what's amplitude? Once again, it's the maximum displacement of a particle from its equilibrium. So amplitude here, where wavelength stretches from the middle of a compression to the middle of a next compression, and amplitude simply stretches from the middle of a rarefaction to the middle of a compression. So in other words, it's half a wavelength. For instance, here, if this was the middle of a compression, an amplitude will stretch from the middle of a compression to the middle of a rarefaction. So you will see here, let me indicate it to you. If it's from the middle of a compression to the middle of a rarefaction, this will simply be an amplitude. Same for this side, middle of a compression to the middle of a rarefaction is where an amplitude will stretch. So amplitude is therefore half a wavelength. Okay, let's look at some important definitions. Once again, what's a compression? It's a region of high pressure in a longitudinal wave. In other words, what does this mean? It means there where the particles are close to one another, while a rarefaction is a region of low pressure in a longitudinal wave, meaning there where the particles are more spread out. What's a reflection? A reflection is when a sound wave collides with an object like a wall and then it's reflected. What is an echo? An echo is reflections of sound waves. But please pay special attention to an echo, because an echo says it's reflections of sound waves. So remember, as you can see here in this illustration here on the right side, an echo is generated when a sound is generated by a source. Let's say the lady is screaming. The moment this lady is screaming, sound waves is going to be generated and they're going to travel. The moment it strikes a wall. It's going to bounce right back. And when it bounces back, it's going to travel all the way back to the lady, and that's when her ears picks up the sound wave and she hears an echo. So remember that an echo is basically a sound wave traveling twice its distance, because it travels when it's generated, it's going to travel, it's going to strike a wall or strike an object, and then it's going to bounce back and travel right back to its source again. So echoes is sound waves traveling twice their distance. But as we are speaking, we are not always hearing an echo. But what's the reason for that? So, if we are standing in a small room with many objects in it, especially soft surfaces like carpets, curtains, blankets, they are soft surfaces. They absorb this sound. So as we are speaking, the soft surfaces absorbs our sound. The moment the sound is being absorbed, no echo is heard. The reason for that is because if the sound is absorbed, it cannot bounce back and return back to our ears. But when do we hear an echo? It's when we are standing in a big room with many empty spaces, and then the hard surfaces like the walls and the ceiling and the floor that's present in this big room causes the sound to bounce off the hard surfaces, and then they can return back to our ears, and that's when we can hear an echo. So remember, a summary: small rooms with many soft surfaces absorb sound. The sound cannot bounce back, and therefore we cannot hear an echo. While we are in a big room with many hard surfaces like ceilings and walls and floors, the sound can bounce off these surfaces and therefore return back to our ears, and then we can hear an echo. Examples of animals that can use or not can use, that do use echoes and reflections, or depends on echoes and reflections, it's dolphins and bats and whales, because they make use of echolocation to detect their prey. What does that mean? You can see here in this illustration, it illustrates echolocation. So this dolphin generates a sound. The sound wave then travels through the water. The moment it strikes prey, for instance the fish, it's going to bounce back and then return all the way back to the dolphin, and then the dolphin can detect whether the prey is close or further from him or whatsoever. So that's echolocation. Once again, an echo generates a sound, it strikes an object, and then it travels right back to the source so that the source can determine where its prey is.